So this is an introductory video on uncertainty. If you know a little bit about uncertainty and you want to refresh what you know, this is a good video to watch. If you've never heard of uncertainty, this is a great place to start. So this is intended for the high school level. It explains the basics of uncertainty. So the first thing I'm going to look at is what is uncertainty and why do we have it? What's the function? What's the purpose? Because it actually is very important, and I think we should understand the importance when we start working with it so we can understand its usefulness. The second thing to look at is how do we write uncertainty? Because there are actually some very specific rules that we use when writing uncertainty, and there's even different forms in which we can write our uncertainty. The last thing is how do we know what our uncertainty is? And I'll show two different examples of how you can find the uncertainty. And there's one final thing that we won't discuss in this video, but it's something really important and crucial to uncertainty, which is how to propagate uncertainty. So for example, if you have two measurements, each of which is a little bit uncertain, then if you take those two measurements and multiply them to produce some new value, then your new value must have some uncertainty as well. So there's rules for how to propagate the uncertainty, how to carry the uncertainty in measurements through when you perform operations on those measurements or with multiple measurements. So those are the rules for propagating, but that's not going to be covered in this video. So on to what uncertainty is and why it exists. Okay, so let's say I'm doing an experiment and I've got some fluid and I want to measure the temperature. So I put a thermometer into the fluid and I read off the value. But because my thermometer is not so good, it's maybe really old and it uses old technology that was not very precise, the reading I get is just 23 degrees. Or maybe I put some fluid in and I get a different reading like 89 degrees. Or it could be something high like 247 degrees, let's say. And what we see is that this thermometer, because it's old and because it's not very precise, it never gives us any decimal places. So it's being rounded to this place, right? Which is the singles place or the ones place. And that's not very good for us as scientists because we want to know, we want very precise values and precise measurements. And so this device, which is not precise, doesn't give us a very good reading. But it's even worse than that. And here's why. If the actual temperature in the fluid is 247.3 or 247.1, then we're just going to read off a value of 247. And if it's 246.8 or 246.5, right, then it's still going to read the same thing, which is written down. So we can see that because we have an imprecise device, that kind of rhymes, imprecise device, because of this imprecise device, there's a range of values that could be the actual temperature. And this device, therefore, it can only measure the value with a certain amount of confidence. In other words, even though I've written down the value is 247, it could be as high as, let's say, 248, and in actuality, it could be as low as 246. That's kind of the range of values that I could have in the fluid. That's the range of temperatures the fluid could have, given this particular reading. So we need a way to reflect this fact. We need a way to show the world and show people who look at our data that this value of 247 degrees has a particular range within which the true temperature lies. And we show this using uncertainty. So what we do is we say the temperature, right, the Celsius temperature, is 247 degrees Celsius plus or minus 1 degree Celsius, or maybe 2 degrees Celsius, or whatever it might be. We're going to see some rules later for figuring out what the uncertainty is. But the important thing now is that this is the uncertainty, right? That is uncertainty. And it indicates a range of values within which we think the actual measurement lies. So we think what we're saying when we write this, that the temperature is 247 plus or minus 1, what we're saying is that the temperature is, well, it's from 246 to 248, somewhere in that range. So that's our introduction to uncertainty. We can start to see uncertainty exists. It exists so we can communicate to other scientists how good our data is, right? So 1 degree Celsius, that actually might be kind of low for some uncertainty. At least let's consider a different example where we have a horrible thermometer, right? And the thermometer can only read, 0 degrees Celsius or 100 degrees Celsius or 200. It can only read in intervals of 100. That would be such a terrible thermometer. It would be utterly useless. And any measurements that we took with that thermometer, they would be completely useless. And the way that other scientists could tell that these readings are so useless is because they would see this huge, giant uncertainty of plus or minus 100 degrees, right? So people make jokes. They say, I don't know, like let's say you ask someone what their age is, and they don't want to be asked their age, so they say, well, I'm 30 years old, plus or minus 20 years, right? That's a big uncertainty in age. That's a terrible measurement. You'd never believe that they were actually, you wouldn't really know much about how old they were if they told you that. And likewise, measurements in the lab that have high uncertainty don't really tell us much about what the true measurement is, right? The higher the range, the worse the data, and the less useful those measurements. So this is why we have uncertainty, to communicate how good our measurements are. And the really interesting thing is that in many modern experiments and labs, the main task that many scientists are after, especially in the world of physics, is to take more precise measurements. Right? People are always trying to reduce the uncertainty in the measurements. And a lot of the time, that's the main goal in science. You're trying to get a better measurement, narrow in on precisely the value, because until we have a really, really good value with really small uncertainty, we may not really know so much about the thing that we're measuring or what it means. So uncertainty, it's not just this exercise that we do in high school. It is perhaps one of the most applicable things that you could learn in a high school science class when it comes to real science and real labs and real researchers, at these research institutions. So the last thing that I just showed you was uncertainty which arises from our measurement devices. Okay, we call that device uncertainty. Sometimes it's referred to as device uncertainty. And device uncertainty is simply the uncertainty resulting from a particular measurement device. And because no measurement device is infinitely precise, right? No measurement device gives us every infinite decimal place. It rounds at some point. Because of that fact, there will always be some uncertainty in any measurement that we do with a device. Electronic devices and analog devices, everything follows in this category. Right? Any device has uncertainty associated with it. And that's important. We'll see some rules in a little bit which allow us to calculate or to know the uncertainty based on what kind of device we're using. But before we go on, I want to discuss a second type of uncertainty which exists, right, which is different from device uncertainty. So let's say we do an experiment where I hold my hand out and I drop a ball, some height, h, and it lands on the ground. And I drop this ball a number of times. I conduct different trials, and in each trial it's dropped from the same height, h, right? And in each trial, I measure the time that it takes for the ball to fall to the ground. And the first time that I measure it, the first trial, my reading is 1.24 seconds. And the next time it's 1.21 seconds. Then it's 1.28 seconds, right? You sort of see what's going on here. 1.20 and 1.29, let's say. Actually, let's give one more, 1.30. So what I've just done is I've taken repeated measurements, right? All of these measurements here, all of these, I've measured the same thing in a repeated way. I've measured it over and over and over. But clearly, there is some spread across the measurements, right? There's a range. In fact, the range is from, well, the smallest value was 1.20 and the biggest value was 1.30. So this tells me that if I'm measuring the time of descent of this ball, then that measurement, it has some uncertainty, right? Because maybe one time I measure it and it's 1.20, or maybe it's 1.25 or 1.29. Basically, it could fall anywhere within the min and max values that I've just measured. It could fall anywhere within those values because of lots of factors, right? Lots of things. Maybe I'm clicking too slowly, or I'm clicking too fast, or maybe my hand moves slightly up and down. There's lots of things that it could affect my value. But basically, what we see is that there's a range, which means there's uncertainty in the measurement, right? The time that it takes for this ball to fall, it has some uncertainty. And another way that we can write the uncertainty is, and let me just say, this little delta sign, right? Actually, let me erase the delta. We haven't discussed it yet, so don't worry about it. The uncertainty for a set of repeated values or measurements is often taken to be half of the range, right? So I look at my data, I say the biggest time was 1.30, right? The smallest time was 1.20. So I say the measurement of time that I have from this data is, let's say, the average, okay? 1.25. And if that's my average value, then the uncertainty would be plus or minus 0.05, right? Because 1.25 plus 0.05 gets me to this, the max, and 1.25 minus 0.05 gets me to the min. So my uncertainty is half the range, which I could calculate by taking the max time minus the min all over 2. Because that would give me 1.30 minus 1.20 all over 2, which is 0.05, plus or minus 0.05. So this is different. This is different from the previous type of uncertainty we examined. Device uncertainty, it arises as a result of a device being not perfectly precise. This, though, we sometimes call statistical uncertainty. Statistical. And it's the uncertainty due to fluctuation in a measurement, right? And we evaluate how big that uncertainty is by repeating a measurement and looking at half the range. Half the range. So this is another way we can evaluate uncertainty by taking by repeating a measurement and looking at the range or the distribution of values that we write down, that we record. So 2 types of uncertainty. So that's another reason why uncertainty exists, because we don't always get the same value when we take a measurement twice in a row. It doesn't always come out the same. So we need to express the lack of confidence we have with uncertainty. We need to communicate that, yeah, I measured it to be We have to be able to tell scientists, other people who look at our data, you have to tell them, yes, okay, I measured it as 1.28 seconds this time, but it could have been as low as 1.20, and the reading also could have been as high as 1.30. Right? So that number, 1.28, it has uncertainty. The general range is from this to this. So that's called a statistical uncertainty, and it exists for the same reason, to demonstrate the confidence that we have in a particular value, and to demonstrate how good our data is, how meaningful is it, how confident are we in the numbers that we're writing down. So we have a special way for writing uncertainty on paper, and it is what we've seen already. Right? Let's say we measure a height, and the height comes out to be 2.1 plus or minus 0.1 meters. And sometimes we write it with parentheses around it like that. Whoops. Parentheses around it. Or sometimes we don't put the parentheses around, and we just write the 2.1 plus or minus 0.1 all really close to each other, like without any spaces. And then we give a little space after the unit. So this is how we write uncertainty. Sometimes there's parentheses, sometimes not. And there are different types of uncertainty that we can write down. What I've written down here, this plus or minus 0.1, that's called the absolute uncertainty. The absolute uncertainty. Right? And it's just the raw value, which has units, right? Absolute uncertainty has units. And the units of the absolute uncertainty are the same as the units of the measurement, or the value. Right? And there's a rule that we use in the high school level about absolute uncertainty. And the rule is that the absolute uncertainty has only one sig fig. Only one significant figure, or one significant digit. So you would never have something like plus or minus 0.15 meters at the high school level. You would always round it to 0.2. Right? So if you're doing a calculation and you find your absolute uncertainty to be this, right, you cannot report it as such. You have to round it to this value. So that's absolute uncertainty. It has units, and it only has one sig fig in the high school level now for what we're learning for our purposes. There's another way we can write uncertainty. Oh, and first let me say, absolute uncertainty has a variable. So let's say that we measured this height. It was h, right? H is 2.1 plus or minus the uncertainty. So what I'm going to do is I'm going to write in the variable we use for uncertainty right here. So here's what we use as the variable. Delta H. That's the variable for uncertainty, for absolute uncertainty. So I would write down here, I would write delta H is the absolute uncertainty, and in that case it's plus or minus 0.1 meters. If I'm measuring velocity, then the uncertainty, the absolute uncertainty, would be delta V. So the delta just tells us there's some range. Sometimes, maybe in college, you'll see it written with a lowercase delta instead of a capital delta. But that depends on what program you go to and what convention they use. So uncertainty. There's another way we could write uncertainty, and it's called the percent uncertainty. Percent uncertainty, or percentage, sometimes percentage uncertainty. And here's the rule for percentage uncertainty. You take it's plus or minus, and we take the uncertainty, the absolute uncertainty, and we rewrite it as a percentage of the measurement, the value. In other words, in this case, it's going to be 0.1 over 2.1, right? The units of meters will be in the numerator and denominator, and they'll cancel out. And we multiply it by 100% to convert it to a percentage. Okay? And we write it down. So in this case it comes to plus or minus, this is 4.8%, and that's approximately equal to plus or minus 5%. Right? So before I said that absolute uncertainty can only have one sig fig. The way that we deal with sig figs for percentage uncertainty is we round to the nearest percentage. That's usually the way it's done in high school. You round to 5% or 18% or 92%. You round to the nearest percentage. So sometimes it'll have two sig figs, the percentage uncertainty, and sometimes it'll just have one, and that's okay. That's fine for this. So there's percentage uncertainty. Now, what we've done is percentage uncertainty is the absolute uncertainty over the measurement, right? So there's no special variable for percentage uncertainty. We just sort of write the variable as this: the absolute over the measurement, over the value. That's the percentage uncertainty. And so we use these two types of uncertainties when we are explaining uncertainty and describing uncertainty. And the reason we need both is because when we get into the rules for propagating uncertainty later on, sometimes the rule requires that we work with the absolute uncertainty, this. So for example, sometimes you have to add absolute uncertainties, but other times, with other scenarios, we propagate uncertainty by working with the percentage uncertainties. So for example, we might add the percentage uncertainties in two values. Right. So there are some rules we can use to instantly know how much uncertainty a measurement has. Right. So what I'm going to show you then, this part of the video is going to explain rules for finding device uncertainty, the first kind that we talked about. Device uncertainty. And just to let you know, device uncertainty is the main form of uncertainty utilized in high school science. Maybe in your high school physics class you will get into statistical uncertainty. Certainly in a college physics class or a college science class that would become important. And I believe also in some advanced bio classes you get some statistical uncertainty. But the main form that we deal with at the high school level, especially in chemistry and also in physics, is device uncertainty. Okay, I have my meter stick here, and it's not a very good meter stick. Let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and a big tick mark, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and a big tick mark, 10. And yes, it continues, 2, 3, 4. Right, so let's say that this is 1 centimeter, and this is 2 centimeters. So each little tick mark is 0.1. Right? And I line up, I'm measuring the height of something. What am I drawing? What is this? I'm measuring the height of a calculator, a tiny calculator, less than 2 centimeters high. And so it's a mouse calculator, right? A mouseculator. And what do mice like? They let's say they're measuring cheese plus cheese, right? That's what they measure in their lab experiments. They just add cheese, and it equals more cheese always. That's what mice care about, finding cheese. So there's our mouse. He's measuring the cheese. There's his tail. And he cannot wait to find that cheese and add it together to make more cheese. Okay. So we line it up, that little mouse calculator, the mouseculator, and let's say it comes to this point, right? And I haven't done a very good job of drawing this, but let's say it's a little bit less than halfway between this tick mark and this tick mark, right? So the halfway point, let's say, is like right here, and it's just under. The Mouseilator is just a little bit under the halfway point between these two tick marks. Okay, so the lowest tick mark, the lower of the two tick marks, is 1 point. Well, we count up 1, 2, 3. So it's 1.3 centimeters. The next one is 1.4. So halfway between the two, this red half mark that I've drawn is 1.35. And we're saying that the calculator, the Mouseilator, is barely below 1.35. So I estimate this last digit, right? I say, okay, maybe it's not 1.35. What if we just call it 1.34, and call it a day. It's 1.34, right? Just a little bit below. The rule for device uncertainty, because we estimate this last digit, and that's how we take measurements in high school science class, we estimate that last digit. So because we're making an estimate, we add plus or minus 5 in that digit. 5 in that digit. In other words, plus or minus 0.05, because we estimated the hundredths place. So our uncertainty is plus or minus 5 in the hundredths place. Like that. 5. And the reason that we add plus or minus 5 is because we say, well, we're really good at figuring out if we are at the 1.3, right? I'm going to be able to tell if it's right at 1.3 or 1.4, or whoops, 1.4. And I could tell if it's halfway between, right? So in other words, if the real value is 1.31, right, or 1.34, I'm not going to say something besides 1.3 or 1.35. So the most that I could possibly be off by is 0.05. Because if it's 1.31, then I would never say anything higher than 1.35. And if it's 1.34, I would never say anything lower than 1.3. And I would never say anything higher than 1.35 if it were at 1.34, like it is. So 5 covers me in all scenarios because I'm good at finding these. I'm good at lining up and deciding if it's at one of those tick marks. So that's kind of the motivation for why we use this. And this is a rule. This isn't just what we do for a meter stick, right? This is a general rule. Anytime you take a measurement with an analog device, this is analog, it's not digital. The rule is that the absolute uncertainty is 5 in the last place. Okay? So in this case, the last place was the hundredths place, so the uncertainty is 5 in the last place, the hundredths place. 5 hundredths. Right? And it's also, another way we could say the same exact thing, is that the uncertainty is 5 in the estimated place. So we estimated this place. All of these others we didn't estimate because we had tick marks telling us exactly what the correct value was. So this is the only estimated digit, or the estimated place. So it's 5 in the estimated place. And that's the rule for all analog devices. Right? If it doesn't have a digital component, then it's analog. Examples, scales, right? The old scales where you have to move the weights around to find the mass. Rulers are really common. Tape measurers, anything where there's no electronics involved, nothing digital. So we've seen the rule for analog devices. Now there's a different rule, there's a different uncertainty rule when we're working with digital devices. And I will show us what it is again through an example. No mouse calculator this time. Okay, So I've got this fluid, I'm measuring the thermometer, and it's a nice big thermometer. And they're reading on the thermometer, kind of a weirdly shaped thermometer, the reading is 21.4 degrees Celsius. There it is, 21. T equals 21.4 degrees. Yes, good. Science. We are taking data. Science. But wait, there's uncertainty, of course. We know there's uncertainty. Because this device is only so precise. It doesn't give us all the extra decimal places, right? We don't know if it's 21.48, 21.37, blah, 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 so forth. So here's how we evaluate the digital device's uncertainty. We say, if the actual temperature of the liquid were 21.5, then the computer would display 21.5, right? So we know that the actual temperature couldn't be more than 21.5 when we see this reading, 21.4, right? Because if we had this as our actual temperature, then that's not what we would see on the screen. And likewise, if the actual temperature were 21.3, well, or anything below 21.3, then we wouldn't see this value, 21.4, on the screen, because the computer already has another way for reflecting 21.3. It's by showing 21.3, right? Very obvious. So in other words, if this is the reading that we see on the digital device, then we know the actual value of the temperature can't be more than 21.5, and it can't be less than 21.3. Because if it were either of those things, then we wouldn't see this. We wouldn't see 21.4. We would see one of these values, right? Or maybe something even higher or lower, so forth. So the way we do digital device uncertainty is we say, this is the rule. We say, the uncertainty is plus or minus 0.1 degrees Celsius. And here's where the 0.1 came from. I didn't just make it up. It's not always 0.1. Here's where it came from in this example. If we add 0.1 to this number, we get 21.5. That's the max. So if we add 0.1, we get the max. If we subtract 0.1, we get the minimum value that the temperature could have, right? So 0.1, plus or minus 0.1, covers us for all of the possible values that the actual temperature could be when we see this reading. And the general rule, right, if we want to extrapolate this out into a general rule, the general rule is whenever you have a digital device and you have some reading, the uncertainty is always 1 in the last place measured by your device. So in this case, my device can only measure to the 10th place. It doesn't measure the 100th place. So it only measures the 10th place. Thus, the uncertainty is 1 in the 10th place, or 0.1. Right? Let's say I had a better thermometer, and my better thermometer was giving me a reading of 21.43. Yes, very good. Better thermometer, good job. And in this case, the uncertainty is plus or minus 0.01. Because now my better thermometer measures to the 100th place. Right? That's the last place it measures. Thus, my uncertainty is 1 in the 100th place. If I had a really terrible thermometer that could only measure to the singles place, or the ones place, then, so if it gave me a reading of 21 degrees Celsius, then now I have to round, I have to say my uncertainty is plus or minus 1 degree, because the last place that it measures is 1, the singles place, so it's 1 in the singles place as my absolute uncertainty. Right? So we can see that the precision of our measuring device, which is simply to say the number of decimal places that our measuring device reads off, is what determines the absolute uncertainty in measurements taken with that device. And this is the rule for digital devices. It's different from the rule for analog devices. There's one last point I want to make about uncertainty. If I tell you that the velocity of a ball is measured to be 5.00 meters per second, and it's measured with a digital device, let's say this fancy thing called a photogate, then because I've given you the value, and because I've told you it was measured with a digital device, you instantly know that the uncertainty is 1 in the last place. Like this. That's pretty cool. Pretty cool. Now, if we go later to rewrite this uncertainty, there's a rule, a special rule we must follow. Okay? Special rule. And here it is. The value or the measurement must always be rounded to the same place as the absolute uncertainty. So remember, absolute uncertainty only can have a single sig fig. And here, this absolute uncertainty is rounded to the hundredths place. Therefore, every time we write the velocity, we have to make sure it's rounded to the hundredths place. These places have to match up. They have to match up. Okay? And that is important. That's really important. So if you go to plug your value into Excel, right? We have a data table, and let's say it's V plus or minus. Let's say we're just writing it like this in our data table. So I've given you V plus or minus, and maybe I also measured, let's say maybe I also measured the time that it took for something to happen. And yeah, I'll write that as delta, let's say I also measured, not the time, but the acceleration, plus or minus let's say 0.5 meters per second squared. Somehow I did something to measure the acceleration. And okay, here we are. If I go to plug in this value, 5.00 into Excel, it's going to round it to 5. That's what Excel does. But if Excel performs that rounding operation, then I've done something illegal. I've done something wrong. I've rounded my value so that it doesn't match the uncertainty. So instead, what I have to do is I have to go into Excel, and I have to tell Excel to add the extra zeros until this place matches this place. And there are ways we can do that. You can hit Control-1. You can choose what the thing is, what the formatting is for the cell. So you can say, whatever this is a number which has 2 decimal places. Or you can change it to a percentage or currency or a date. There's lots of options in there. Or now, on the newer Excel, there's a button in the ribbon, the top ribbon, with all of those little buttons and shortcuts. There's a button that allows you to add zeros to a value. So you do that. You add the zeros so that your places match up. And that's really important because we have to follow the same rule when we go to propagate our uncertainties. And when we propagate our uncertainties, these values may not always match up. Oops. This place and this place may not always be the same. So, important rule. There it is.